we were saying that more complicated systems where the dominant poles are, meaning the rightmost poles in the complex plane, uh, can often characterize the behavior of the system. Where the where the dominant poles are, can often be used to characterize a more complicated system's behavior. And we said the rule of thumb is that all the non-dominant poles and zeros should be at least a factor of 4 to the left in the complex plane for this to work very well. Let's look at where it's within a factor of 4 and how bad it is. Say here's an original second order system. And here was its step response in blue. Then I started adding poles. This one's 4 times to the left. You know, this guy has a complex pair of poles at -1. This guy has a real pole at -4 or 4 times to the left. This guy is at -3 or 3 times to the left, 2, 1, and at this h(1), the extra pole is on the real line exactly where the complex pair is. And let's see what happens. Blue was the original. Here was a factor of 4 away. Not super good, but I want to be a factor of 5 away. 3, 2, you know, that's quite a bit of, if you're talking about peak overshoot, that's a pretty big difference. This guy's up here at about 35% overshoot. This guy's down here at about 10, something like 8. 35% versus 8%. It's a pretty big difference. And by the time you've got the pole and all the poles lined up, you're getting back to close to a first order system. In fact, you could sort of model it with either set of pole, either the real pole or the complex pair here. Probably still not that good a match. But that's what happens with an extra pole. Peak overshoot moves down and to the right. You also get a slower response, rapid response, east bar thing. What about an extra 0? I did the same kind of thing. Started with the same system, then added a 0 that's 4 times to the left, 3 times to the left, 2 to the left, and right on top of it. Blue again was the original. Get down here with about a 35% peak overshoot. 4 was a little bit above that. Peak was higher and to the left. The closer you get to the real pole, the higher the overshoot and the more to the left. So you get quicker responses, but a lot more overshoot. And you can see these are pretty big differences. But if you know about those differences, you might be able to accommodate for them some. Here was an extreme case. We'll get into it later, but if you have any poles in the right half of the complex plane, you're going to get an unstable system. All the time domain specifications don't matter. Well, they're irrelevant. What about the zeros? What about zeros in the right half plane? Well, here's a case. Zeros are in the right half plane. You not only get, it doesn't match your actual system, you get it actually initially totally wrong direction. So we can't really use dominant pole concept if that's the case. So zeros near the dominant poles have huge effects, and to the right of the right half of the pole, dominant poles, and into the right half plane are really bad. The right half plane means wrong direction. So this stuff only works if the non-dominant poles and zeros are to the left of the dominant poles. If they're almost on top or to the right, kind of all bets are off as far as approximation. The extra pole tends to move the peak overshoot down and right. Extra zero tends to move it up and left. If there's a pole and zero near each other, they kind of cancel each other's effect. At least if it's all in the left half plane. You can't depend on that in the right half plane. And zeros to the right of the dominant poles are in the right half plane, totally mess things up. So these are just some tidbits to kind of remember and know qualitatively or intuitively. You don't have to memorize, or there's no formulas involved here. Let me see if I can go through a whole design process. Actually, I'll save this for another video.